Alright guys, we'll get started. Okay, so last week... last week we were talking about simplification. Excuse me. How do we go from a truth table to writing down Boolean algebra expressions, and then we can build the circuit, or we can use Boolean algebra to simplify those expressions and build a simpler circuit, or, as we'll see the rest of this lecture, we'll use counter maps instead to build a simpler circuit. So that's what we're trying to do in all of this lecture, is basically build a circuit with as few gates as possible by using some tools at our disposal, tools such as truth tables, sum of products, product of sums expressions, Boolean algebra, and or counter maps. And by the end of this lecture, we'll have finished the content on how to build simple circuits so circuits that only do one thing, and you'll be able to get started on project part A and part B. After the end of this lecture, you'll have everything you need to start working on the project. And after I finish the lecture slides, I will continue on with going through the project and hopefully get through to building the circuit for question 2 of the project. Alrighty, but first a review of what we did last week. So we talked about standard expressions. And standard expressions is just one way of writing down using Boolean algebra, the circuit that we want to build, but doing it in a standard way. And there are two kinds of standard expressions: standard sum of products and standard product of sums. Neither is better than the other. You can use whichever one is the most useful for you in that situation, unless of course you're asked otherwise. So here is the standard sum of products expression that corresponds to this particular truth table. Here is the standard product of sums expression that corresponds to the same truth table. So even though these equations may look very different, they are actually equivalent in the sense that if you build a circuit that does this expression, and if you build a circuit that does this expression, both circuits will do exactly the same thing. In fact, there's many, many, many expressions you could write down that also correspond to this truth table that will also produce a circuit that does exactly the same thing. So the choice for you then, in terms of which expression do I use to build my circuit, is going to be the one which is easiest, either the one which uses the fewest number of gates, or the one that uses only 2 different kinds of gates rather than, say, 4 different kinds of gates. Whatever is going to be easiest for you to build, that's the Boolean algebra expression that you will use of all the choices. Okay. So, generally speaking, while standard sum of products and standard product of sums are very useful in terms of writing down a Boolean expression for the truth table, most of the time they're not going to be the best expression for building a circuit. And that's because you can do some Boolean algebra simplification on both of these in order to get to a simpler expression. It won't be a standard expression anymore, but it will be a simpler expression. Okay? So while these are useful, they're more of an intermediate step. You can do some Boolean algebra after you have written down the standard sum of products or standard product of sums to get to an expression that you're then going to use to build a circuit. Okay. Now, just a quick reminder, it's called a standard sum of products because every product in the sum has exactly the same number of terms as there are in the domain. So if my truth table has 3 inputs, every product term has 3 inputs, and every product term corresponds to a row of the truth table where the output is 1. So a standard sum of products, there's a product for every row of the truth table where the output is 1. And that product is chosen so that whatever combination of inputs corresponds to that row will cause that product term to be 1. So if I substitute 0, 1, 1 into this product term, it will be 0 bar 1 and 1, which will be 1 and 1 and 1, which will be 1. So this combination of A, B and C will make this product term 1. This combination of A, B and C will make that product term 1. This combination of A, B and C will make that product term 1, and this combination of A, B and C will make that product term 1. And that's how we write down a standard sum of products from a truth table. And we can go backwards too, of course. Now, our other option is a standard product of sums. Now, when we do a product of sums, we're actually now looking for the rows of the truth table that cause the output to be 0. So when we're doing a product of sums, we will have a sum for every row of the truth table that causes the output to be 0. So if I have a look at this sum, it will be 0 if and only if A and B and C are 0, because 0 or 0 or 0 is 0. So this sum corresponds to the first row of the truth table where A, B and C are all 0. This sum here will be 0 if A is 0 and B is 0 and C is 1. So a C value of 1 will cause A or B or C bar to be 1. So this sum term corresponds to this second row of the truth table. This third sum term corresponds to this third row of the truth table, because if A is 0, B is 1 and C is 0, then A or B bar or C will be 0 or 0 or 0, which will be 0. So the key thing to remember, when you're writing down a sum of products, you're looking for rows in the truth table where the output is 1. When you're writing down products of sums, you're looking for rows in the truth table where the output is 0. Okay. How is the x equal in both cases? By definition. So because x is exactly this column. So by definition, x is 0 for each of these combinations of inputs, and this you can trial and error if you like, but this expression is always 0 for this combination of inputs and only those combinations of inputs. And by definition, if you look at this equation, this x is 1 only for these combinations of inputs and 0 for all other combinations of inputs. So by definition of standard products, sum of products and product of sums, these expressions correspond exactly to this value of x for all possible combinations of inputs. Any other questions? All right, so that was a quick review of standard sum of products, standard product of sums. Now let's talk about Carnot maps. So we saw last week how to create a Carnot map. So let's go to this example. So we saw last Thursday that a Carnot map is actually just another way of representing a truth table. The information in a Carnot map is absolutely the same as the information in a truth table. It's just that the entries are reordered in a little bit different way, and the different way that they are ordered is so that we can have a grey code encoding of the rows. So this square here corresponds to the combination of ABC, where A and B are both 0 and C is 0, which means this entry here corresponds to this row here. So I'm just copying across the value of x for this row into this cell. Similarly, let's take a look at this square here. It corresponds to the combination where A and B are 1, 0, and C is 0. So I'm looking for row 1, 0, 0. If I look for row 1, 0, 0, it's this one. So I've just copied across the 0 value from x from the truth table into that cell, because that cell corresponds to that row. Okay. Any questions on this revision of how we go from a truth table to a Carnot map? And if we have 4 variables in our domain, so if we have 4 input columns in our truth table, we can create a 4x4 Carnot map, which we saw here. So here's a 4x4 Carnot map that we would build if our truth table had 4 inputs into it instead of 3. Above that, we won't do in ELEC1710. We will only go up to 4. Okay, so we saw that. Now, why are we bothering with a Carnot map? And this is the key point, so that we can do, by-step our Boolean algebra simplification and use Carnot map simplification instead. It's a 2-step process. The first step is that we group all of the ones. So we create some groups, some circles, such that every entry inside the circle that we draw must be 1. And we want those groups that we draw, those circles that we draw, to be as large as possible. And we want there to be as few of them as possible. And once we've done that, once we've drawn all those groups, we can use those groups to write down a simplified sum of products expression for our truth table. When I say simplified, it means it's going to have it's not like a standard sum of products where you have every variable in the domain in every product. You're going to try and do the opposite now. You're going to try and have as few variables in the domain in the SED product as you can. And that's what's called a simplified sum of products expression, and we can get that directly from the Carter map. So some things to be aware of when you're drawing your groups is that these 4 cells, this one, this one, this one, and this one, correspond to a group of 4. These ones correspond to a group of 2. These ones correspond to a group of 2 because we allow our Carter maps to wrap around. So we imagine that the top and bottom edges are actually touching, and the left and right edges are actually touching. So we allow our Carter map to wrap around, and that's a key thing that people miss when they're drawing Carter maps, is to look for some wraparound adjacencies. All right, so here is finally, putting that all together, here's how we do our simplification. Here's our truth table for some expression for x. We create the Carter map, so we've just copied across the entries that are 1 in each row of this truth table to the appropriate cells in the Carter map, and similarly for the zeros. Then we do our grouping. So there's a group of size 2 here. There's a group of size 2 here. And this one is all by itself. It's not adjacent to any other one. So if we go right or left or up or down, every adjacent cell to this cell is 0. So we just have a group of size 1. So here are our groups. A group of size 1, a group of size 2, and a group of size 2. Now, if we have a group of size 1, then there's not any simplification we can do there. We just write down the product that corresponds to that particular cell. So it's as if we're doing a standard sum of products. So groups of size 1, we can only do the standard sum of products representation for that group. There's nothing more we can do. But when it comes to groups of size 2, we're not going to write down the standard sum of products, so we have a product for this one and another product for this one. We're going to join them together and find a single product which represents both of these cells and only both of these cells. So if you have a look at this group of size 2, you can see that they have in common that B is 1, and they have in common that C is 1. But every possible value of A, 0 or 1, is allowed for this group. So we could have written down BCA or BCA bar, but that would take too many terms. We want it simpler than that. So we're just going to write down the values that all of these ones have in common, which happens to be B equals 1 and C equals 1. So the product term for this group is B and C. If we have a look at this group of size 2, same thing. The variables that this group have in common, every entry in this group has in common, is that A equals 1 and B equals 1. So the product term for this group is A and B. Now we just write down all of those product terms we've found and we OR them, so we have a sum of products expression. But it's called a simplified sum of products expression because we could have written down 4 of these standard products, each with 3 variables in it, but we've simplified it now so that we only have 3 products and 2 of them only have 2 variables in it. Okay. And this is in fact the simplest expression, simplest sum of products expression you can get for this truth table. You cannot do any simpler than this as a sum of products. If you draw your groups correctly in your Carter map, you will always get the most simple sum of products possible for your expression. And that's why we use Carter maps. Any questions? So let's have a look at a few examples for where you can find groups. The best way to learn Carter maps is just to practice with them, and I'll do some more Carter maps when we work through the project. But some patterns to look out for. We've just seen this one. This one here, there's a group of 2 here, there's a group of 2 here, and also a group of 4 if we don't forget the wraparound adjacency. So why didn't I draw a group of 4 here? Why didn't I draw a group of 4 around these 4 cells? Because there's a 0. That would not be a valid group because I'd be grouping some cells that had a 0 in them. Can't do that. Okay. Why didn't I draw a group of 3 around these 3 and then a group of 3 around these 3? That's right. The size of the group has to be some power of 2. So it has to be 1 or 2 or 4 or 8. Otherwise, the adjacency rules won't work in terms of writing down our product, our simplified products. So the group can only be size 1 or 2 or 4 or 8. I want the biggest group I can get without there being any zeros inside that group. So over here, I can draw a group of 4 here. I could have drawn a group of 2 here and I would have covered all the ones, but I would not be satisfying the rule of making the groups as big as possible. So I'll cover these cells twice so as to allow me to get a larger group of 4 here. Now, I could have done a group of 2 using these 2 cells here. That would have been a valid group, but this one would have still been left by itself, so I had to draw this group of 2 anyway, which would have made this other group of 2 redundant. So there's no point adding in redundant groups of 2 because that means I'm going to have redundant products in my sum of products and it won't be the simplest expression I could possibly write down if I have some redundant terms. It will still be a correct expression. I can add in, as long as the groups are valid, they will be valid terms, but there will just be unnecessary extra terms in my sum of products, which will then make it more difficult for me to build the circuit. So you want those groups to be as large as possible so that the expression will be as simple as possible. And here's another one to look out for, a wraparound adjacency on the sides this time. So these 4 plus these 4 are a group of 8. And if we look at this group of 8 and we say, okay, so what values of A, B, C and D do all of these entries have in common? We can see that they all have D equal to 0, but they have every possible combination of A and B and every possible combination of C. So this entire group is just represented by the product term D bar. Because the one thing all of these entries have in common is that D is 0. Okay. And if we have a look at this group here of 4, they both have B is equal to 1 in common and they have C equal to 0 in common. So this group is represented by the term B and C bar. Okay, and then you do that for every group and then you write down the sum, the OR of each group's product, and then you have your final simplified sum of products expression for that counter map. If you wanted to create the standard sum of products you could, you would just need to write down a separate term for every single one in this counter map. So you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you could write down the standard sum of products, which would have 11 products in them, each product with 4 variables in it. But we don't want to build that circuit, so instead we're going to use counter maps and do the groupings to write down the simplified sum of products, which only has 3 products in it, and there are fewer variables in each product. Okay, any questions? Yep.
Let's say if we have 6 group.
A group of size 6?
Yeah.
That would not work.
Yeah. So should we use 4 and 2?
Very good question. So let's say if we had a group of 6, the question was, do we use 4 and 2? So let's have a group of 6. Let's suppose there was a 1 here and a 0 here. So we had 1, 1, 1, 1, 1, 1. Would we have a group of 4 and a group of 2? Or would we have something different? 2 groups of 4. Excellent. We would have this group of 4 and another group of 4. Because we want our groups to be as large as possible. And if they're overlapping, that's fine. Yep, so 2 groups of 4. Great question. Yep.
Let's 1, 1, 1, like the only one row is 0.
So one of these ones?
Yeah, one of those ones. And all of the entries are 1 except the bottom.
So everything is 1 except these are zeros?
Yeah.
Yep.
By your definitions of how you define the thing, you'd need at least 2 expressions.
Correct.
But if you just had a knot of where all the zeros were.
So that's so let me repeat that question because that's a really good question. So the question was, suppose all of these 6 entries here were all 1s and that these 2 entries were 0. Now, we've just answered that question that we need 2 groups of 4. So a group of 4 here and a group of 4 here. And then we have a sum of products where we would have the product for this group, which would be A bar, I think, yep. And then we would have the product for this group, which would be B. So we would have A bar or B would be my expression. Okay, everyone agree with that? Didn't make a mistake there? So then the question was, well, why would you do that? Why don't you just group the zeros and write down an expression for those because there's 2 of those? And my answer would be, yes, you could do it that way. And what would you get? So if we were to say these 2, now we'd have to do product of sums now, not sum of products, because we're grouping zeros. So that's really, really important. I've seen people group zeros and then write down a sum of products expression for the zeros. That's not going to work. Because remember, in the truth table, if we're searching for zeros, what we're searching for is a product of sums term. Now, if I did write down the product of sums term for those 2, what would it be? For these 2 terms. So if I wrote down the product of sums, this one is, so now what's the combination of A, B and C that would make that 0? It would be A bar or B or C. And this one would be A bar or B or C bar. And then I could do some simplification and I would actually end up with exactly the same expression I got from doing the grouping.
But couldn't you just say a knot all over the top of A?
Oh, okay, yep. So you could say, all right, let's not draw the truth. Let's not do sum of products for this truth table. Let's do sum of products for the opposite truth table where I place every 1 with a 0 and every 0 with a 1 and then put a knot across it. Yeah, you could do that. So you could say, okay, say my counter map has 1, 1, 1, 1, 1, 1 and then 0, 0. Then we create another counter map which is the opposite of that, and that counter map will have zeros everywhere except here. So there'd be a 1 here and a 1 here. Yep. And then I'd group those, and that would correspond to the term A, B bar, A and B bar, but I'd put a knot across it. So I'd have A and B bar, bar. Then I apply De Morgan's theorem, and what have I got? The exact same thing. So yeah, there are multiple different ways you could come at getting the same expression. All of them, as long as you are clear on what you're doing and don't get confused, oh, I inverted the counter map, so therefore I have to invert the Boolean algebra expression. It should all come out to exactly the same expression. But until you're confident in what you're doing, I recommend you just stick with one way, and that one way is group the ones and then write down the sum of products expression for those groups. But yeah, once you get familiar with it, there are tips and tricks you can use to try and make things a bit quicker. But counter maps actually are really straightforward. So if you draw a counter map, you get the minimum sum of products anyway, straight away. So that's always a good default way, just to do the standard counter map. Later on, if you really want to save a gate here or there in your circuit build, you can be a bit clever by using De Morgan's theorems or other options to try and save a gate by, using knots by inverting terms and things like that. Yep, you can do that. If you're really running out of space on your breadboard. Cool. Any other questions? All right. So if we do all of these things, cover all the ones at least once, maximize the size of the groups, and minimize the number of groups, we are guaranteed to get the sum of products, which has the fewest possible variables in it and the fewest possible sums, which is called the minimum sum of product expression. So if I ask you for the minimum sum of product expression, you can find it using counter maps. You could also find it using Boolean algebra 2 by simplifying until you can simplify no further. But if you get to the point where you can simplify no further, you have a sum of products that can't be simplified any further, then you have what's called the minimum sum of products. And the counter maps is the easiest way to actually find that. So let's do an example. Use the counter map here to simplify the expression. This is a chance for you guys to have a go, just to confirm that you are very clear on what you need to do. Please ask me any questions if you have any. Has anyone got the expression?
Isn't this similar to the previous one? B bar plus A bar plus C bar plus AC?
It could be. Don't know the answer yet. I haven't done it. Not exactly the same, I don't think. Alright, it looks like some of you are finished. So let's fill in the truth table. Fill in the counter map using just copying across the truth table. So the first row, first square is 1, second row, second square is 1, third row, third square is 1, third row, fourth square is 1. Now the next row, the fifth row actually corresponds to the square down here. The fourth row is 0, the fifth row is 1, so it corresponds to this square down here. The sixth row is 1, which happens to correspond to this square. The seventh row is 0, which corresponds to this one. And then the final row is 1, and the final row corresponds to that square. So I filled in the counter map. Now I need to do my groupings. What's the largest size group that you can see there? A group of 4? Excellent. And the group of 4 is from this wraparound adjacency. Did someone say they saw another group of size 4? No? What? So there's my group of 4 from the wraparound adjacency. Now I have these 2 entries left over. I still need to cover those, so I need to add at least one more group. There's no group that can cover both of them. That means I need to add at least 2 more groups. One group to cover this one and one group to cover this one. The largest group I can draw, which also covers this one, is a group of size 2. And the largest group I can draw, which also covers this one, is also a group of size 2. So now I have 3 groups, and they're all those groups as large as they can be. So I write down the product term that corresponds to each group. Now this red group has in common that B is 0, so its product term is just B bar. This group here, this blue group here has in common that A is 0 and C is 0, so its term is A bar C bar, and this one is AC. Okay. Anybody get something different? Anyone have any questions about the process?
Could you just say which letters map to which groups again?
Okay, so this red group, what does it have in common? It has in common that B is 0. So all these 4 squares have in common that B is 0, so this group corresponds to B bar. This group here has in common that A is 0 and C is 0, so it corresponds to A bar C bar. And this green group here has in common that A is 1 and C is 1, so it corresponds to the product term AC. Okay. All right, so last week we remember that alarm problem that we did. We wrote down the Boolean algebra expression for the alarm, and then we did some Boolean algebra simplification to come up with a very simple circuit. And we're going to repeat that now, but instead of using Boolean algebra, we're going to use Carnot maps. All right, so the first thing is I'm going to put this expression into my standard sum of products form. If you can go straight to the truth table from this expression, that is fine, please do. If it's easier for you to first put it into standard sum of products and then create the truth table, that is also fine. So instead of creating the truth table, I just went straight to the Carnot map. You can do the truth table first and then the Carnot map if you like. But if we go from our standard sum of products straight to the Carnot map, it's exactly the same process as for when we went from our standard sum of products straight to the truth table. We look for each cell that corresponds to each product term, and for each product term in our expression, we put a 1 in the corresponding cell. So this product term corresponds to the combination A is 0, B is 1, C is 0. So A is 0, B is 1, C is 0. So this first product term corresponds to a 1 in this cell. And we can repeat that for every single product term here. So there's 1, 2, 3, 4, 5, 6, 7 of them. And 1, 2, 3, 4, 5, 6. Why do I have 7? Should there be 6? Have I repeated one?
No, there are 7.
Yeah, there's a repeated one.
Yeah.
Sorry?
There's not B, not C.
There is a repeat. Okay. A not B not C. Let me write that down so I can fix it after the lecture.
It's repeated because it gets expanded from 2 places.
Yeah, and I haven't noticed it. So slide 32. Excellent. So one of these terms I can cancel out because it's been repeated. So there should only be 6 of them, corresponding to these 6 ones in the Carnot map. So this is not standard sum of products because I've got an extra product, but I shall fix that. All right, so I've got my Carnot map. Now I'm going to do my groupings.
If you look at the function, we have 3 equations where we need to add 2 variables, as in like A not B gets converted to A not B C and A not B not C.
Yep.
So those are 6 terms, then 1 is the previous one, that not A, B, not C. So we should have 7 terms.
We should, but remember from our rules of Boolean algebra that if we have A or A, then that's equivalent to just having A. So any repeated term, we can remove one of the repeats if we're ORing them together. So using Boolean algebra, having repeated terms is fine. This expression is still correct, but we don't need a repeated term because it doesn't add anything. All right, so we actually only need, this is correct, but I've just written the same term twice, which is not particularly helpful when I'm filling in the counter map. All right, so here's my counter map. Here are my products that are 1, and here are my products that are 0. Let's do the simplification now using the counter map instead of Boolean algebra. So I draw my groups, group of 4, and another group of 4, which is not shown. So there's actually 2 groups of 4, one here and one here. Let's look at this group in blue. What does it have in common? Well, it has in common that A is 1. So this group corresponds to the product term, which is simply A. And this group here has in common that B is 1. So it simply corresponds to the product term B. And I can write down my simplified sum of products for F using the counter map, and it's just A or B, which hopefully is exactly the same simplified expression I got last time when I did it using Boolean algebra. And it is, so that's fantastic. Now, both methods using Boolean algebra or using counter maps are both fine. You can use whichever one you prefer, unless it's an assessment task and you're asked to do a specific one. All right, so any questions at this point about using this counter map to replace Boolean algebra simplification? All right. Now, there's one extra thing that counter maps are very useful for that you can't necessarily do with Boolean algebra, and that's something called don't care conditions. So sometimes we might build a circuit where we don't care what the circuit does for a certain combination of inputs, either because those inputs are guaranteed never to occur, or because we literally don't care what the circuit does if those inputs do happen to appear. You could say, I don't care, so I'll just make it 0. Or you could say, I don't care, so I'll just make the output 1. You could do that, that's totally fine. But if you actually use the fact that you don't care about the output for that combination of inputs, you can end up with a simpler circuit. And so let's have a look at that with an example. So in the labs this week, you are using a BCD to 7-segment display decoder. You're using one of those chips. Now we're going to build one. So you just got the chip from the bench, plugged it into your breadboard, and used it without worrying about what was inside. But you did know how it functions. It takes in a 4-bit input, which is the binary value of a number, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and it outputs the correct 7-segment display values to turn that number into a display. So if I enter 0, 0, 0 as my 4-bit input to a binary 7-segment display decoder, it should output a 1 on every segment that corresponds to 0, so all of these, and a 0 for this segment. So it should output 1, 1, 1, 1, 1, 1, 0 if I input 0, 0, 0. And if I input 0, 0, 1, which is the binary for 1, it should only turn on these, output the appropriate values so that only these 2 segments turn on. And so on and so forth, all the way up to if I input 9, 1, 0, 0, 1, it should turn on all of the segments except this one. So this chip does that for us, and we use that chip in the lab to do that for us. But now we are going to actually design that chip ourselves, as if we were designing a binary 7-segment display decoder ourselves, rather than just pulling one off the shelf. Okay, but the difference for the decoder we're going to build right now is that we're going to say, okay, if the binary for 10 or 11 or 12 or 13 or 14 or 15 comes in, I don't care what it displays, because I know that in my circuit, it happens to be an alarm clock, say, I'm never going to tell it to display on a single 7-segment display 10 or 11 or 12 or 13 or 14 or 15. They're simply not BCD inputs that I'm going to need when I build my alarm clock. So I'm going to tell my decoder that whenever you see those inputs, 10, 11, 12, 13, 14 or 15 at your input, I don't care what your output is. I could have said make your output everything off. That would be one valid decision to make. I could have said, actually, why don't you just output A, B, C, D, E, or F? So we could use this to display actually the value, you know, the hex value. So I could say, have a BCD do hex display decoder. I could have made those choices. But no, I'm making another choice, which is in my design, that actually if you get 10, 11, 12, 13, 14, or 15 as your binary input, display whatever you like. It's never going to happen, so I don't care. So I actually literally don't care what the output is for that combination of inputs. And that's where we get don't care conditions. Okay, so let's have a look at all the conditions I do care about. And we actually saw this when we went through the project last week. So decimal 0, we want to turn on every segment except G. If we want to display a 1, we want to turn on B and C, so on and so forth. If we want to display an 8, we need to turn on every single segment. So this here is exactly what I want my decoder to do. If it gets these inputs, I need all of these outputs to be 1. And I can draw that in a truth table. So if the input is 0, that corresponds to 0, 0, 0. This should be my output. If my input is 8, which corresponds to 1, 0, 0, turn all the segments on. Okay. And you can go through this table and verify one step at a time that these are the outputs I want for these combination of inputs, but we sort of did a similar thing last week for the project, so I won't go through it. And if I make the decision, what about the combinations 10, 11, 12, 13, 14, 15? If I make the decision, actually, I want the segments to be all off for those combinations, then I actually get a Carnot map that looks like this. So these, in red, these 6 cells correspond to inputs, which are 9, 10, 11, 12, 13, 14, and 15. And if I make the decision, actually turn off the 7-segment display, so I want my outputs to be 0, then this is what it will look like. So, just like in the project, I'm going to have to build a separate circuit for every single letter. But let's look at segment A first, and let's do the Carnot map for segment A. So if we look at segment A, it's going to turn on for 0, for 2, what else is it going to turn on for? 3, 5, 6, 7. So it's actually going to turn on for all of these, but it's going to be off for 1 and 4. So if I have a look at these blue entries in my Carnot map, it's going to turn on for all of the combinations 1, which were they? 0, 2, 3, 4, no, 0, 2, 3, 5, 6, 7, 8, and 9. So all of the A, B, C, D inputs that correspond to those numbers it's going to turn on, and only for 2 of them, 0, 0, 0, 1, which corresponds to 1, it's going to turn off, and 0, 1, 0, 1, which corresponds to 5, it's going to, no, is that 5? 4, it's going to turn, wait a minute, no, 1, 0, 0, of course, 4. 0, 1, 0, 0, 4, it's going to turn off. Okay, so these are the two values, 1 and 4, where that segment A has to be off. These are the segments where it has to be on, and these are the inputs that we don't care about. These are the inputs that we don't care about because they're numbers greater than 9, so we're going to set it to 0. All right. Do some groupings. Here are some different groupings we can do. There's a group of 4 here, there's a group of 2 here, there's a wraparound adjacency with the group of 2 here, and there's a group of 2 here. And we can write down our simplified sum of products for segment A. And now we can build our circuit for segment A, and then we can repeat the whole thing again for segments B, C, D, E, F, and G, which I'm not going to do. Just giving you segment A as an example to show you the benefits of don't care conditions. So this is my simplified sum of products for this particular design decision where I want the segment off for inputs greater than 9. That design decision has led me to this simplified sum of products, which is actually not that simple. But nonetheless, we can build that circuit and that segment A will behave as we wish. All right, but what if I made the other choice and said, actually, for these inputs, 10, 11, 12, 13, 14, and 15, I don't care what each of the segments do, whether they turn on or turn off. So this is the don't care condition. This is what my Carnot map for segment A is going to look like now. So my Carnot map now has 3 different kinds of entries. I put a 1 where I need that segment to turn on, which are all of these inputs. I put a 0 where I need that segment to turn off, which was 4 and 1. And all of the others, I put an X where X stands for don't care. So I don't care if that segment is on or off when I have that combination of inputs. Now that I draw my Carnot map, I can use those X's to my benefit. So I can include those X's in a group if I want to, or I can leave them out of a group if I want to. Because I don't care, I have some flexibility here. If they help me draw a bigger group, I'll put them inside a group. If they don't help me draw a bigger group, I'll leave them outside a group and they can become a 0. So now, when I draw my groups, I actually only have 2 zeros, this one and this one. Everything else is either 1 or X. So instead of a group of size 4 here, I can actually draw a group of size 8 by including all of these X's. Because that decision of including those X's in the group lets me do a bigger group. Same thing over here. I think I had a group of size 2 before. Now I can turn that into a group of size 8 by including all of these X's. I can also use the corners now. I can use all the corners to do a wraparound adjacency of a group of size 4 instead of what I think I had before was a group of size 2. So by using these X's, when I want to, I can make my groups bigger, which means I can make my sum of products expression simpler. Now these are not the same circuits. These are not the same circuits. This circuit will turn the segments off when I have 9, 10, 11, 12, 13, 14, 15 input. This circuit will potentially turn them on or off depending on how I draw my groups. So these are not the same circuits. I've made a different design decision and I've decided that I don't care and I've built a simpler circuit because I don't care about those outputs. So that's the value of don't care conditions in Carnot maps. It allows you to simplify things if you truly don't care about the output for certain combinations of inputs. Yep. I'll talk about that after the break. So I'll have a 5-minute break now, and when I come back, I'm going to talk through the rest of the project, going through finalising question 1 and showing you how to build the circuit for question 2.
So like,
if you have an XOR gate available. Yes.
so can't all gates only simplify to the limit of like possible times?
Yeah, so Kano maps give you a sum of products. Do away with sum of products. And it's the simplest sum of products you can find. It's not necessarily the simplest circuit you can find. And I'll talk about that a little bit. It's a bit nuanced. But yes, if you have A bar or A bar B, you could recognise that you could do that with a single XOR gate. Now, because gates come in packets of 4, so have you done the lab yet? Oh no, you're doing it next week. Never mind. So we saw last week that if you buy a chip of AND gates, it's actually got 4 of them in them. Right? So maybe when you're building your circuit, depending on what else is in your circuit, it might actually be better to build this one because although you've got 2 AND gates and an OR gate, you might already have those spare. You might already have some chips there with some spare gates. Whereas this one, you have to put in a new package of XOR gates and maybe only use one of them. So which one is better is actually context dependent.
But it's a simplified algebra beyond common maps.
Yeah, if you wanted to, yes, well, I guess this is really algebra or just recognising that that's an OR gate. The answer is this one simpler than this one? So the answer is actually neither. Depends on your definition of simpler. In terms of amount of gates, this is simpler. In terms of amount of integrated circuit chips, you might need a circuit. Yeah. So I think technically this uses for your gates if you just want to draw it, but if you want to build it on a breadboard, I don't know which one is going to be better. But yeah, the Kano maps will only give you the simplest sum of products version. If there's a product of sums version that's simpler, it won't give you that. Alrighty. So this week on Tuesday, I started working through the first question in project part A, and we talked about how what our circuit was going to do was going to take a 3-bit input, and depending on the integer value of that 3-bit input, was going to select the corresponding digit in my student number and just turn on the correct segments to display that digit. So it's a little bit like the BCD to 7-seg decoder that we just saw, but it's a specialist BCD to 7-segment decoder designed just for your student number. Won't be of any use to anyone else, but if you want to output the digits in your particular student number, this decoder is for you. So what we did was we came up with these are the steps. Step 1, write out the truth table. We did that last week. Step 2, write out the expressions, either standard sum of products or standard product of sums from the truth table, and simplify with Boolean algebra, or use counter maps. So whichever way you want to simplify it is perfectly fine, but you do need to include the working out for your simplification in the report, whether that be the Boolean algebra or whether that be a picture of the counter map with the groupings circled on the counter map. So we've done step 1. This is hopefully the same truth table that I came up with on Tuesday. And B and C, yep, that looks like the same truth table. And then I need to write down the Boolean algebra expressions, one for each segment. So let's have a look at what we had. Is that going to come up? All right. Okay, so this is exactly what we drew on Tuesday. For each possible combination of inputs, these are the digits that we need to display. So these are the segments that we need to turn on and turn off to display the digits in that particular student number. Now I need to build a circuit for each of the segments, A through to G. So I need to write down Boolean algebra expressions for each of those segments. All right, so let's start with A. That one is easy. A is always 1, so we don't really need to do anything more. You don't need to show me any more working out than that if the column is, you have a column that's all 1s. Now B, I could write down a standard sum of products or a standard product of sums and then simplify with Boolean algebra. But since we've just been doing counter maps, let's do B using counter maps. So we'll draw a counter map. So we have 0, 0, 0, 1, 1, 1, 1, 0. Always remember to put it in grey code order. So there's every possible combination of my switches, switch 2, switch 1 and switch 0. Now if I have a look at B, I'm just going to copy across from B to my counter map. So it's 0, 1, 0, 1, 1, 1, 0, 1. So I've copied my truth table for B to my counter map for B. Now I'm going to draw my groups. Here's a group of size 4 and a group of size 2. So now I can write down my expression for B. So B equals S0 is this group, or S2, S1 bar is this group. So there's my simplified expression for B. All right, let's look at C. Now C has only got a single 0 output, so I'm going to use product of sums because that's nice and easy. There's actually only one sum. So I want the sum, which will be 0 for the combination of inputs 0, 0, 0, and the sum, which will be 0 for that particular combination of inputs, is simply S2 or S1 or S0. So there's my expression for C. All right, now let's have a look at D. Again, I only have one 0 output for D. So let's do a product of sums again for D. You can do the counter map if you like. In fact, I actually recommend that you do 2 methods and check that you get the same answer. It's always a good way to check your work. But let's do D. So there's only one 0, so I can write down the sum that corresponds to this particular row. So the sum that will be 0 for this combination of inputs is S2 bar or S1 or S0. So there's my expression for D. Let's have a look at E. So E's got a mix of 0s and 1s, so I'll probably just do the counter map. Let's do the counter map for E over here. S2, S1, S0, so we have 0, 0, 0, 1, 1, 1, 1, 0. I know it doesn't fit, I'll move it up in a second. And we have 0, 1. All right. Can we see that? Yeah. So let's try I'm going to copy across, what am I doing here? I'm doing E, so it's 1, 0, 1, 1, 0, 0, 1, 1. So there's my counter map for E. Let's do my groupings now. So I have a group of 4 here, and I have a group of 2 here. Now this group of 4 corresponds to S1 being 1, and this group of 2 corresponds to S2 being 0 and S0 being 0. If I make a mistake, I'm doing this really quickly, so I will make mistakes. If you see one, please let me know. So there is my expression for E. So I've got A, B, C, D, E. Let's look at F. Now, I think F was the same as D, wasn't it? Is that correct? Yes. So F is the same as D. I don't need to derive that again. And in fact, when I build my circuit, I'll use the same gate. I'll use this OR gate just once and use it to feed both D and F in my Logisim. All right, and finally G, that's got a nice mix, so let's use a counter map for G as well. So S2, S1, S0, 0, 0, 0, 1, 1, 0. You can't, yeah, I'll shift it up in a minute. Just let me.
Can't you just do a simplification because it's repeating pattern with size 4? So you're just going to consider S1 and S0.
S1 and S0. So you're doing the Boolean algebra simplification in your head, and that is totally fine if you can do that. I'm going to do it the long way though, because it'll be easier to follow. I'll do the Boolean algebra next if you like, but let me do the counter map first. So we're doing G. So can you see that counter map? Yep. So I'm just copying across that column G, which was 0, 1, 1, 0, and then 0, 1, 1, 0. So there's my counter map for G. And I can see a group of 2 here and a group of 2 here. So I can write down my expression for G. So what does this group have in common? Well, it has S1, S0 bar. And then my other group has S1 bar, S0.
So how did you get S1, S0 bar?
Did I make a mistake, did I?
No, I'm just confused.
Okay, so I'm doing this group.
Yep.
So what does this group have in common? What do all the entries in this group have in common? Well, they all have the S1 is 1 in common, and they all have the S0 is 0 in common. And so that's how I write down the product expression for this group. And then the same thing for this group. I'm looking at what variables they have in common, and that gives me the simplest product term for that group. All right, now I can do those in different ways. So I think your question was about group G, was about segment G. Can you restate the question for me?
Can you not just do it as a 2-variable thing because it doesn't depend on S? Because it doesn't depend on S2.
So G doesn't depend. Oh, G doesn't depend on S2. Oh, I see what you're saying. Yes, you're right. If you have a look, so what you're saying here is the pattern of the top 4 is the same as the pattern on the bottom 4. Therefore, G doesn't depend on S2. So you could just take S2 out of it and build a circuit based on S1 and S0. But if you have a look here, that's exactly what we've done by doing the counter map simplification. Now, there's one other thing I can notice here, in that this expression here is actually an XOR. So that's equivalent to S1 XOR S0. It's because an XOR is true if S is 1 and an XOR is true if S1 is 1 and S0 is 0, or if S1 is 0 and S0 is 1. So this expression here is the expression for an XOR. So I'm not sure which one of these is going to be easier to build, but when it comes to building my circuit, it may well be that I could replace this whole thing with an XOR gate and I could save myself some space. So that is a design decision I could make later on when I'm building my circuit to save gates, if I'm allowed to use XOR gates, of course. If I'm building this on a breadboard, it will all depend whether I have the XOR chips available to me. If I don't, I would have to build this one. And so that is actually related to a nice question I got in the break, which said, you said Kano maps will give me the simplest possible expression, but this expression is simpler than this expression. So, what did you mean by that? So what I said actually was Kano maps will give you the simplest sum of products expression. Kano maps will always give you a sum of products, and it will always be the simplest possible sum of products. But that's not to say you could use fewer gates by using an XOR or even using a product of sums. Kano maps will give you the simplest possible sum of products, which is usually fairly simple and a good place to start. But if you're really desperate to save space on your breadboard when it comes to building your circuit, you could use either Boolean algebra or your knowledge of gates to come up with some other way that's not a sum of products that will actually save you gates. Okay, there's always that option. All right. Okay, so that's project question 1, and then all we need to do is build it in Logisim. And I showed you that. Unfortunately, this room doesn't let me have 2 screens on at the same time, which would have been great. But, so I've built all of those expressions I just wrote down. I've built them here in Logisim using the gates, so the AND gates and the OR gates. Now, in this particular case, I didn't use an XOR, but I could have, for G, replaced these 3 gates by an XOR gate. So let's do that. So I want a gate that is an XOR gate, and it was XOR of S1 and S0. So, it's 2 inputs. What did no, I don't want 20 inputs. I want 2 inputs. Okay, so what did I say? S1 and S0. So this one is S0, and this middle one is S1. And I could have had, let's see if it is the same. All right, and we saw this working last week, so depending on whether we put in a 1, we got the 9. If we put in a 3, we got a 0. If we put in 2, we got a 6. And you can see for every possible combination, these bottom 2 are exactly the same. So it is equivalent to replace this whole thing by an XOR gate. So let me do that. Oops, I have to go back to circuit edit. And there's my circuit for that particular student number if I'm allowed to use an XOR gate, which I am in question 1. All right. Any questions then about how you guys might go away and do question 1 for your project? Yep.
Do you get all marks for the most simple circuit?
Yes. So there is, the marking guide is on Canvas at the moment, so you can have a read through it. But yes, there is a mark off, I think, if you don't simplify as well as you can. Now, if you failed to use an XOR gate and the demonstrator doesn't notice it, then that's fine. They're more going to notice obvious things, like you're using the same AND gate to do the same thing twice, when you could have just... So, for example, here, this OR gate, I'm using it twice, once for segment D, and once for segment F, because remember when I wrote it down, those segments had exactly the same expression. Now, if you had two separate OR gates doing exactly the same thing, I'm pretty sure the demonstrator would notice that, and you'd probably lose a mark for not using as few gates as possible. Yep. Yep.
The computers, or is there computers at the university that have Logisim already downloaded on?
So the computers in EE104 do. It's a little bit tricky. If you just type Logisim in the search bar of those computers, it won't find it. But if you go to Canvas, in Canvas I've got, the PDFs on Logisim that you use to practice Logisim. It's in the lab page. Right above there, I've written the path that you go to on the lab computers in order to get Logisim. Logisim is also free. There's a link also on Canvas for you to download it and install it on your own PC. I do know that a couple of people with Macs have an issue because of Java. It uses Java. So if your Mac has an issue with a certain version of Java, it might have an issue with Logisim. As far as I know, EE104 is the only room that has Logisim already downloaded. If anyone's having an issue, either they've got no computer at home that can do it, let me know and I'll get Logisim installed on 107, 108 in the EE building, because those rooms are freely accessible to everyone during business hours. So let me know if you have an issue and I can get it installed on those computers. But most years, even the Mac people have found a workaround. But if not, let me know and I'm happy to do that. And it's only some Macs too. Most Macs are fine. I'm not sure what is special about certain Macs that causes a problem though. Any questions? Any other questions? Okay. Now let's look at question 2. What do I want? PC. Now, question 2. So in previous years, we've just done question 1, and then the students have built a circuit on a breadboard to implement question 1. But the problem with that is that there were an awful lot of gates, and and if you've wired up the lab this week, you'll know that gets a bit tedious with just one IC on the board. So you can imagine if you have 6 or 7 of them, it's going to be a bit of a nightmare. So what I've done instead is question 2 is now going to be a simpler version of question 1. And it's the version where you only are going to display the last 4 digits of your student number. And by only displaying the last 4 digits, that means you only need 2 switches now. So 2 switches will select between 4 digits. So 00, in this particular case, 00 will display 7, 019, 106, and 110. So you're going to design a new circuit that's just displaying the last 4 digits. And when you do that, and when you build it on a breadboard for part B, it's going to be much easier for you to build it. All right? So you still do question 1 and do the full thing with Logisim, but question 2 is going to be a simpler circuit so that when you build it on your breadboard, you won't go crazy, hopefully. All right, so this is the problem, similar to before, but only the last 4 digits. Now, the steps you want to go through, though, are the same. So let's go through it. So step 1 is always truth table. And this time I only have 2 inputs now. I'm going to call them AB because the subscripts were getting frustrating. So let's call them AB. And I have 4 combinations. But I still need to output all of the correct values on all 7 segments for those 4 combinations. So I still need A, B, C, D, E, F, and G. But what I'm actually going to be doing is just copying down now the last 4 rows of the truth table I already did. Because in the truth table I already wrote down how to do, so for me it's 7, 9, 6, 0. I already know what a 7 is just 1, 1, 1, and everything else is 0. A 9 is everything is 1 except E. A 6 is everything is 1 except B. And a 0 is everything is 1 except G. So you can start to see already how your circuit's going to be a little bit simpler. So there's my truth table now for my question 2 circuit for this particular student number. Now yours will be different unless you happen to have that same 4 combination of digits. Okay, any questions? All right, now you don't need to show the working out for this in your report. It's not, you just need to show all of the working out for question 1. Question 2, I'll assume that you know what you're doing since you've already done it successfully for question 1. All right, but I'm going to do it anyway. So A is equal to 1. B, I've only got 1 0 there, so let's do the product of sums. So what combination of A and B will give me a sum that is 0? So that combination is A bar or B. C is just equal to A, which is equal to 1. D, again, there's 1 0, so let's just do a sum. So the combination of A and B is A or B. So if A is 0 and B is 0, the output will be 0. Let's see what else we've got. That was D. E. Now I could do a counter map with E and do a grouping, but I can tell just by looking at it that my output E will be 1 when A equals 1. So E is equal to A. Then F is actually the same as D. And now G, now G is an interesting one. It's going to be, it's the same as before. It's going to be my XOR. So it's going to be A or B bar. Oh, sorry, A and B bar or A bar and B, which we saw just a minute ago was the same thing as A XOR B. All right, so those are my expressions for my circuit for question 2. So let's build it.
Sorry, what was that last bit? A bar times B.
So A B bar or A bar B.
And then you said, that's
The same as A XOR B.
right.
Yeah. Because as was noticed before, the top 4 rows of the truth table 4 were the same as the bottom 4 rows, and now we're doing the bottom 4 rows. So that's why G is the same. All right. So let's do this. Okay, so we need 2 inputs. A and B. All right, and we need a 7-segment output. So we go to input output, and you choose the 7-segment display, not the hex digit display, which is a slightly different one. We want this one. So there's my input and there's my output, and I'm going to be drawing these expressions I already derived. It's a pity I can't display both at once. So I said A was equal to 1. That was my first expression, if you remember. So let's just put in, so I go to wiring now, and I'm just going to pick power. So power, or VCC, remember that 1 just corresponds to a high voltage and 0 corresponds to a low voltage. So for 1, I'm just going to put a high voltage in. Now from memory, come on. Sorry, I'm terrible with the mouse on a mouse pad. I just cannot do it. So that is A. So trial and error here. Put in a high voltage to all of the pins and you'll figure out which pin lights up which segment. This particular pin lights up segment A. So we have A is equal to 1. Alrighty. Now B, what do we say for B? B is A bar or B. So that means we need an OR gate. We also need, so that's a 2-input gate. We also need a NOT gate. All of the common gates are across the top here. So what did I say, A bar or B? put it there and move that down one. So A bar or B. So that is the circuit I need for segment B. So I'm just building the gates that correspond to the Boolean algebra expressions I just worked out. And I'm pretty sure that B is that one. Very good. Now C was also equal to 1. So let's, now I think C is the second one from the left. Yep. So there's C. Now D, my expression for D was A or B, so I need another OR gate now for D, which this time was A up, so 2 input. So A or, that was B, this one will be A. So there's A or B, and that's going to be my D, which should be this one. Let me just check that I've got that right. Very good. Now, E, my segment E, when I worked that out, it was just equal to A. So let's pull, go back to editing my circuit again. Let's pull A out. Okay. Let's check that that was segment E. Did I got that right? Yep. Okay, now F is the same as D, which was A or B, so I'm just going to use the same output. Now I think F is this one. Let me check that. Perfect. And last but not least, now here's where my choice for G comes into it. I can do A and B bar or A bar and B, or I could use an XOR gate. Now, when I'm building the Logisim, I already have 2 OR gates. So adding another OR gate is not going to mean, when I build my circuit on a breadboard, that I need a whole nother chip, because one integrated circuit chip has 4 OR gates on it. So I already have, to do what I've done so far, I already have IC on my breadboard, which uses 2 OR gates and has 2 OR gates spare. So I already have that there waiting to go. So adding another OR gate is not going to take up space on my breadboard. Same thing, I already have an integrated circuit package with NOT gates in it. So there are some free NOT gates there ready to go. So adding some more NOT gates is not going to make my circuit more complex. But I haven't used any AND gates yet. So if I wanted to do A and B bar or A bar and B, I would need to add an integrated circuit packet with some AND gates on it. My other option, using the XOR, would mean that I needed to add an integrated circuit packet with some XOR gates on it, because I also don't have any XOR gates. So in both cases, I'm adding another chip to my board, but with the XOR, I'm adding another chip and using 1 gate. So that's going to be a bit easier for me than the other option. But depending on what else was on my breadboard, that might not necessarily have been the choice I made. So you may make different choices in this situation, depending on what's already available on your breadboard. But let's go with an XOR. So XOR is not a standard gate, so I'll look inside gates. Make sure I get the right one, XOR. And it was A XOR B. Wait a second, it's a 2 input XOR. I'm not sure why the default is 5. I think it should be 2. Okay, so A XOR with B is my final segment. So let me wire that up. Now hopefully, unless I made some mistakes, I should now be able to show you that this circuit will display the last 4 digits, 7960, of my student number as I put in the inputs. So 00 gives me a 7, excellent. 01 gives me a 9, excellent. 10 gives me a 6, and 11 gives me a 0. So I'm done. I've successfully done question 2. Now, I haven't quite done though, because if you read through the instructions in question 2, it says that when you build it in Logisim, you actually need to use the chips, so the integrated circuit packages, which will make it easier for you later to build it on a breadboard. So, where is that? Here are the instructions. So Logisim, when you install it on your PC, doesn't already have the 7.4 series library already there ready to go. You need to download it from the website, which the link to the website is given in the project documents. You go there, you choose the 7.4 series library by a particular person's first name is Ben, can't remember his last name. It's there in the documentation. You download it, and then inside, somewhere on your computer, it doesn't matter where, and then inside Logisim, we now choose to use that library. So we go Project, Load Library. We want a Logisim library. Now, where would I have put that? Oh, you can't see this. Excuse me one moment. So we go Project. Can you see that? Yes, you can. Project, Load Library, Logisim Library. Now I have to remember, I think I put it in Downloads. Come on. Okay, so that's where I downloaded it to. Obviously it'll be different on your machine, wherever you downloaded it. And we open it up and we can see it appears here. So here are all the possible packages that correspond to the integrated circuits that you're actually going to use in the lab. All right, now I wish I had dual displays. You will need to have this slide in front of you as you're doing this. So this slide gives you a lot of information for how to use these packages. First of all, it gives you the number. So that's the number you need to use if you want an AND gate. And it also tells you which pins are which. So I'm going to be looking back and forward to this slide from now on as I build my circuit in Logisim. So, what do I need? I need some OR gates, and if I look back over here, OR gate is a 7432. So let me get a 7432. And there's my chip that corresponds to the package, which has OR gates in it. Now I'm going to flip that facing, let's go north, yep. So I'm going to line them all up so they're all facing the same way with the little notch on the left. And that's going to be easier, that's going to make it easy for me to build it when I go to my breadboard. I want them all lining up in the same way so that the VCC is all in the same spot, ground is all in the same spot, and I can directly look at this slide and the pins will line up exactly and I don't have to do rotations in my head when I'm trying to wire it up. So I suggest you do the same thing, it makes it much easier. So I know I need some OR gates. I know I need at least one NOT gate. So that happens to be 7404. So let me put in a NOT gate. And, oops, come on, let me line it up so it's facing the same way. So there's my NOT gate. So I need a NOT gate, I need OR gates, and I need an XOR. And that happens to be 7486 is the number for that. 7486, very good. Get that facing the same way. All right. So in Logisim and also in the lab, the first thing I'm going to do is give power to these chips. These chips won't work unless they're powered up. So let me put in some VCC and connect it to pin, yep.
One thing I noticed is that for question 2, you're not allowed to use XOR.
Oh, did I say you're not allowed to use XOR gates this year, did I? Okay. That's all right, that's good then. That means if someone does happen to have the same 4 digits as me, they can't just copy what I'm doing. So, yeah, okay, I didn't realise I changed that. Thank you for pointing that out. So you can't use XOR gates. I'm going to build it with XOR gates, but then we could remove this chip, put in an AND chip, and we could build the circuit to make it work for question 2. All right, I'm going to keep XOR gates because I want to show that these two circuits are the same. So first of all, I power them up. So pin 14 it is on every single, oops, oh I hate mouse pads, is going to be connected to VCC. Oh, didn't happen. Okay, and now I need to connect to ground also on each one. I need to connect pin 7 to ground. So ground. Okay. Oops. All right. Now I'm going to use the same switches for inputs as I used in my first circuit, and that's going to help me show that both circuits are doing exactly the same thing. All right. Now let's recreate this circuit at the top, but now down the bottom using my gates. So first thing I need to do is feed A into a NOT gate. And if I look at my 7404 package over here on my slide, I see that I can use pins 13 as the input and pin 12 as the output for the first NOT gate. So let's take A, which is this one, and let's, come on you silly thing, let's feed it into the first NOT gate. So there's A, and then out of here is A bar. Now what did I need A bar for? I needed to feed that into the first OR gate. Now the first OR gate is over here, so that's the input for the first OR gate, that's the second input for the first OR gate, and that is the output of the first OR gate. So I had A bar going in, but I also had B going in. So let me feed B to this OR gate. This is where it gets really important, particularly on the breadboard, because nothing will blow up in Logisim, but particularly on the breadboard to make sure that if you think you're connecting to an input, you are, and if you think you're connecting to an output, you are. All right, so here's my first OR gate, the two inputs. Now the output of that OR gate goes into, on Logisim, I'm just going to use exactly the same 7-segment, and then on the breadboard, it will just be the same 7-segment chip you've already used. Input, output, 7-seg. So I'm just going to take the output of that OR gate and feed it through to, where did it go? The last one, I think. For B. All right. So I've done this now. I've done this part using a NOT gate and an OR gate. Now let's do this second OR. This OR was A and B, so it's A or B. So let's take A again. This one was A, wasn't it? So the second OR gate is just next to the first OR gate. So that's the first input, A. Now B was this one, so B. And then the output from my second OR gate goes into, where does it go? Okay. Goes into that pin on my 7-seg. All right, so I've done the second OR gate. Let's do my XOR now. So it was A and B again. I've already just done A and B, which happens to be, this one is A, this one is B, and then the output of my XOR went into the top. All right. Now let's put in this, my second OR gate. The output from my OR gate I used, the second OR gate I actually used twice. So let's do the same thing. Let's use it twice, because it fed 2 segments, if I recall. Oh, I also had a VCC input for A. Oh, it's getting messy. Let me...
Why do you need the ground to the center segment?
Pardon?
Yeah, you need that ground to the center segment.
Instead of your XOR output, you put
Oh, I saw it. Thank you. I would have noticed that eventually. I really don't know why I did that. That was a brain phrase. Yes, no, I will need the output from the XOR to go into there, not the ground. Thank you very much. That's the input. Let's have a look at my XOR. No, 13 and 12 are inputs, 11 is outputs.
Oh no, it's just you accidentally grabbed it.
Oh, I accidentally grabbed it. Okay, so that's my output of my XOR, which goes into this very first pin. Okay, good. Excellent, thank you guys. So here's my VCC, and it's getting messy. So I was... Let's not do it. Let's take VCC across the top. And where did I need VCC to go? I need it into segment A. And I also need it into here. Alrighty. Now this, I remember this segment was just A, this segment here. So I need to connect up to A, which is this one. All right, have I missed anything, guys? So in theory, these 2 circuits should be doing exactly the same thing. And it's possible I write out something wrong. Let's test it to see. So 0, 0 should give me 7, excellent. 0, 1 should give me 9. 1, 0 should give me 6. And 1, 1 should give me 0. Now the only reason it worked first time this time is you caught my mistake before we got here. If I'd left that mistake in and kept going, here is the point where I'd figure it out. And by doing both circuits in Logisim, it would be really easy for me to figure out where I went wrong, because I can see exactly what colour each of the wires needs to be for exactly each combination, and it would show me which wires didn't line up between the top 2 circuits. So that's why I always like to build both, using the standard gates first, so it's easier to see, and then using the chips second, so that you can, match between the 2. What you need to submit is only this bottom one, but I do recommend doing the top one anyway, to give you, just for the debugging that happens later. Right, so any questions about building the circuit for question 2? Yep?
Are we going to be working on the project in the labs, or will you have separate labs?
No, well the project you'll actually be working from at home, because it's on paper design and or on Logisim, which you can get for free. So you can just do that at home. I mean, you're welcome to do it in the labs if you wish. However, the second part, which is building this circuit on a breadboard, there is, when project part A is being marked, it'll actually only take you 5 minutes to be marked. The rest of that 2 hours, you'll be building this circuit on the breadboard for part B, and then you'll be demonstrating the following week. Say again? I do, but let's have a look. So if you go on to Canvas, let me switch inputs. If you go onto Canvas, then you'll see, I'll show you the schedule now because I think some people have missed it. So if you go to modules and you go to schedule, everything should be outlined here. What we're covering in the lectures, what what you're doing in each IELTS session, and when things are due. So in week 6 IELTS session, project part A will be being marked. And by marked, I mean you'll be pulling up your LogiSim circuit and running through it like I just did to show that it displays your student number. And project part B, you'll be putting down your breadboard, flicking the switches, and showing that it displays your student number. And so you have to turn up to your scheduled IELTS session to get marked. If you submit the paperwork, you do need to submit the paperwork for Part A by the deadline, but it won't be marked, the paperwork won't be marked until you turn up in the lab, and it'll be marked at the same time that you demonstrate, if that makes sense. So you need to turn up to those IELTS sessions in week 6 and 7 and 10 and 13 in order to have your project marked. The paperwork's are due 8 a.m. Monday, and that's fair for everyone because the first IELTS session is 8 a.m. Monday. And then it's marked in whatever lab you happen to be enrolled in. Cool. Good luck, everyone. No worries. See you next time.
I have one question on the student number side of things.
Yes.
Mine has 2 5s in the last 4 digits of the student number.
Yep.
So would I just repeat, I
Those
wouldn't...
two rows would just be the same.
They would just be the same.
And I'll make this
I just
really
connect them
simple.
to the same. We figured that would be the case.
Oh, no, you don't connect them to the same. It's only the segments that are the same. The outputs
Yeah,
are the same.
yeah.
But it will make your truth table significant.
Okay, sweet. Cool. Thanks.
Yeah.
So for developing question 2,
Yep.
are we allowed to use the labels? So can I label the games?
Yes. I should have done that. Yes. That is exactly what you should do.
Make it so much easier. No, that's the XOR, that's the OR.
Yeah, that. And also, I would actually label them with returns. I didn't bother to do a 3 gate.
I think they're like 2 inputs.
Yeah, so if I had an OR, so that OR gate, I would actually would have labelled it with A or B. And that will help me a lot. I mean, I can see if I look in, but once you get more complicated circuits. But yeah, I might mention that next week.
Thought about that. Then someone else asked the question. Someone else asked the question, and then everyone started packing up. I was like, okay.
Yeah, they're always good.
Yeah, so last week, I don't know if you remember, but I had the issue with the MacBook and LogiSim.
Yes,
So, no, I've been able to download a version called LogiSim Evolution. And I don't know, I looked it up, and they said it's essentially the same, except LogiSim Evolution isn't subordinating or something like that.
Okay.
So, do you reckon I'd be right to just use that? It's still made by other people that make LogiSim.
Yeah, sure. If it works, the only issue is we will have to bring the laptop into the lab to be marked because just in case the LogiSim evolution file doesn't load into LogiSim.
Yeah, too easy.